let's see if we can find delta G for this reaction. So what's the first step, do you think?
I'm going to say split it up into half reactions.
Okay, so let's split it up into half reactions. So I've got the iron, and it's going to go to iron 2 positive. I see the iron here going to the iron 2 positive, plus 2 electrons. I do not have to play any nasty games like oxygens and hydrogens.
Nope.
And then the copper 2 positive is going to go to copper, and that'll be plus 2 electrons. I like this one because guess what?
It's 2 and 2.
The electrons cancel, so N in this case will be
2.
2. So it'll be Fe plus Cu2 positive. You don't actually need this, but
No,
for the
we already
reaction.
have it above it.
Plus, oh yeah, Fe2 positive. It
now it's
canceled,
balanced.
but we didn't know that it would actually balance. Right. And so now we do need to look up the values for the voltages for this.
Yes, we do.
So let's go back a
to
couple
the
of
table.
screens. And so we have copper to copper plus 2.
Uh-huh. So let's see. Where is that one? Right.
No,
Nope,
that's the
that's not
wrong
it.
one. Oops, I have the wrong ink color for this, don't I?
Still looking
Mr.
for copper. You guys have probably already seen it right now. Why can't they see it? Oh, there it is, second from the top on the right-hand side.
Point
0.34
for the copper one. Okay. So the copper one is 0.34. The iron to iron 2.
Okay, now this is, well, we're going to see those iron 2 to iron, so we're going to have to flip this one because these are all reductions.
I see it right here, Mr. Sam.
There it is, yep, so that's negative 0.44, but we need to flip it, so it's going to be positive 0.44.
0.44, so that adds up to 78.
0.78, yep.
Now, folks, we're going to use this cool equation. Delta G equals negative N F E naught.
Yep. Now, shouldn't there be a little 0 above that G as well? Since it's standard electrical potential, should be our standard.
Now, we are making an
delta G.
assumption. What assumption are we making?
That everything is at standard conditions.
Which
1 molar solutions and 25 degrees Celsius, 1 atmosphere.
N was 2, right?
Yep.
Times F, which is 96,485.
I don't know why I remember that number.
And then E naught is 0.78. Now, I'm not putting units on there, but we'll put it at the end here. And you get a big number, Mr. Sams.
1.5.
Negative, right?
Yep.
Negative 1.5.
0.517.
0.517. That's way too many significant digits.
Yeah,
by the way, that's going to be in joules per mole. So if we divide by 1,000, you get negative 151 kilojoules per mole. I could do that in my head.
Yep.
All right. So that is the value of delta G.
There it is.
Not terribly difficult.
Not at all.
Okay. Now, what happens? So that's how you solve for delta G.
Yep.
Okay. All right, so on that last problem, folks, we found delta G, right? We found delta G to be negative 151 kilojoules per mole.
G with a little 0 on it.
Yeah, thank you.
Yep.
Now, one thing that we've already kind of talked about this in our last unit in chapter 16, but I want to make sure you can make this connection, folks. And we forgot to put this in your handout, so why don't you're going to have to add this. Okay? So if I want to solve for K, you might remember an equation from chapter 16, which is delta G naught is equal to negative RT natural log of K. So if I know the value of delta G naught, I can solve for the equilibrium constant K. Remember, for double arrow reactions, right? Well, so I can say, now the important thing to note here is this isn't kilojoules per mole, but R, what's R? It's 8.3145 joules per Kelvin mole. So I've got to convert this to joules.
Yep.
So I'm going to say negative 151,000 joules per mole is equal to negative 8.3145, I'm not going to put the units in there, times the temperature. We have to pick a particular temperature, so let's say 300 Kelvin or something like that.
Sure.
Times the natural log of K. Now, how would I algebraically solve that?
I would say divide both sides by 8.3145 and 300.
Now, when you do that, folks, actually negative.
Yes.
Make sure that you divide on your calculator.
Yep.
Do not say divide and then times.
Unless you use parentheses.
Unless you're using parentheses appropriately, yeah. And so what do you get there?
60.5.
We have a negative and a negative, and so that makes it a positive. So 60.5 is natural log of K, and so you have to take e to the 60.5 to get rid of the natural log. You get a big number.
You're going to get 1.95 times 10 to the 26th power.
That's a very high number. Now, what does that mean when you have an equilibrium constant that's that large?
That it's insanely spontaneous.
Yes.
It just goes.
Yes. So if K is very bigger than 1? Very bigger than 1? If it's much larger than 1, then the products are favored. In this reaction, they are very, very favored. Okay? All right. Now, what are we going to talk about now?
The Nernst equation.
Nernst. Mr. Nernst. That sounds like a weird name.
Nernst.
All right. Mr. Nernst said, what happens if you don't have standard conditions? What if it's not 1 molar?
Yeah.
And 1 atmosphere and such? Well, guess what? There's this equation. It's the Nernst equation.
Nernst.
And so if you have a different concentration, E, notice there's no 0 on this E. This E is equal to the E0. That's the number from the standard. And this is essentially over here the correction factor. Now, R is a constant. F is a constant. N is those moles, and T is the temperature. But if you assume a couple of terms, you can assume, for example, if you assume that R and T, if you assume that T is 25 degrees Celsius, R, T, and F are all constants.
Yeah.
And so this right here, if you assume 25 degrees Celsius, you can rewrite the equation, and it looks like this. Now we need to talk about what this Q business is.
Q is your conditions that are not standard.
Or your reaction quotient?
Yeah, you're just going to plug in the concentrations. It's just like K, where you have products over reactants, except instead of using the equilibrium products over reactants, you're going to use
the non-equilibrium.
The given products over reactants.
So here is a particular problem. We have a reaction here that I think we need to do balance first. Yeah.
Yep.
What is the electrically following cell with the following concentration? So I need to balance this equation. Well, not exactly.
We can even just look them up on
we
our
can say VO2 positive goes to VO2 positive. How's that for you? Okay, but now we can go back to that table.
Yeah.
So if we go back to the table, I can find my VO2. This is the one we couldn't find. Here it is, down here.
About halfway on the left-hand side.
Yeah, I think I see it there. All right, so they're right about here, and it's 1 volt.
1.0, look at that.
So now I go, so have you got it down, Mr. Sams? So you guys know where we're going to get this. Mr. Sams got the book out, and we'll just use his book. So what are our options there? Tell me the whole reaction.
You want the whole reaction. Okay, we're going to add 2 hydrogens and 1 electron to the left.
Plus 2 hydrogens and 1 electron on the right?
And on the right, we need 1 water.
Water, okay.
Okay.
And our second reaction, that was 1 volt, right? Was it written? Is it 1 or negative 1?
1.00, positive.
Okay.
As written.
As written. And then the zinc.
Yep.
Zinc is going to go to zinc 2 positive.
Yep.
Plus 2 electrons, and that's actually, I don't have to do any math on that.
Yep. And that's in the
you
book.
Flipped it.
Yeah. In the book, it's negative, so we're going to do positive 0.76.
So the voltage is looks like
1.76.
1.76 volts. Now we do need to then add these reactions, right?
Yep.
So this one we're going to double because we have to get the 2 electrons to cancel. So this will be 4H positive plus VO2 positive.
2 of them.
2 of them, I knew that. Plus the zinc metal makes the zinc 2 positive plus VO2 positive.
2 of them.
2 of them, I knew that. Plus 2 waters.
Just making sure. Just check.
All right, now we have a balanced equation.
There it is.
Now the reaction quotient will be the products over the reactant.
Right, and those are given to us here.
So zinc 2 positive times VO2 positive squared because of the 2 here. Now what do we do with the water there?
It's not really going to participate.
Why?
So, it's not an aqueous thing. These need to be homogeneous equilibriums. So,
so this needs to be
dealing with
AQ.
ions.
And so then we'll say VO2 with a positive 1 charge, kind of weird how that works, times the hydrogen to the 4th power. And the zinc is a solid, so we ignore that. So this is the Q, and if you look up here, we're given all these numbers.
We're just going to plug those numbers in.
So we're going to just plug these numbers in, and we're going to solve for Q.
Plug and chug. Should we...
The zinc 2 positive, 0.1, all right? The VO2 positive, I'll get my things right, is 1 times 10 to the minus 2 squared. I think we'll just find Q first. I think it'll be easier.
Yep.
And the other VO2, the one with a subscript, is a 2 molar, and we'll square that. And the hydrogen concentration is 0.5, and we'll take that to the 4th power. So, Mr. Sams, when you get that on your calculator?
Yep, I got 4 times 10 to the negative 5th.
So it's 4 times 10 to the negative 5th. Okay. So here we have, what was that number again, Mr. Sims?
It's 4 times 10 to the negative fifth.
So